Alright, so here's a nice exercise. So, let's see here. Basically what we want to do is we want to prove monotone convergence, but for functions which don't necessarily need to be always positive. So, but we also have this other condition that the integral of g1 minus d mu is finite. So, as we might expect, because we have this g1 minus, a good starting point is to break each gn into its positive and negative parts. Now, since gn increases to g, gn plus 1 is going to be bigger than or equal to gn. And so that tells us that gn plus 1 plus is going to be greater than or equal to gn plus. Because it can only be increasing. And the only way for this not to be true would be if you imagine if gn plus and gn minus were like arbitrary functions. You could imagine a scenario where like gn minus is really big and gn plus is really big, but then but so that holds, and then gn plus 1 minus is 0 and gn plus 1 plus is smaller than gn plus 1. It's smaller than gn. No, let's see here. Basically, the idea is that the only way that this could not hold would be if you somehow had cancellation between the gn pluses and the gn minuses, which cannot happen because gn plus and gn minus are defined so that they are supported on disjoint sets. Meaning that if gn plus is positive, then gn minus is 0. If gn minus is positive, then gn plus is 0. And so therefore, because gn increases to g, so the gn's are always increasing, if you look at gn plus versus gn plus 1 plus, it can only go up. Because that's going to be the only thing that's contributing to the increase from gn to gn plus 1. At least in any domain. This is at any point where gn plus 1 is allowed to be strictly positive. If gn plus 1 plus is 0, then gn plus must be 0. And so you don't get any increase. So anyways, this is true. And so then we can just apply monotone convergence. The integral of gn plus d mu will increase to the integral of g plus d mu. So, yeah, this is just the positive part of g. Okay, so we use monotone convergence. Now we got to deal with the minuses. So next, gn plus 1 is greater than gn. So the opposite is going to happen here. For when we look at minuses, gn minus, or let's say gn plus 1 minus is going to be less than or equal to gn minus. So as n increases, the gn minuses actually decrease. And so, the integral for any n, the integral of gn minus d mu, well, gn minus is less than or equal to gn minus 1 minus, which is less than or equal to ... which is less than or equal to g1 minus. So this is going to be less than or equal to the integral of g1 minus d mu, which we know is finite. Okay, so we have a sequence of functions, gn minus. They converge pointwise to a function g minus. And all of these functions in the sequence, their integrals are bounded by the integral of g1 minus, which is finite. And so we can apply dominated convergence. So by the dominated convergence theorem, alright, we have, so that I get to go to the next line, the integral of gn minus d mu will converge to g minus d mu. And since the gn minuses are decreasing, this integral will decrease. And thus, if we look at the integral of gn d mu, this is going to be, we can break this up as the integral of gn plus d mu minus the integral of gn minus d mu, because we just break up gn into gn plus and gn minus, and then we break up the integral because you can do that with finite sums. So gn plus is going to increase, or the integral of gn plus is going to increase to the integral of g plus, and we know that minus the integral of gn minus d mu, we know that the integral of gn minus d mu is going to decrease to the integral of g minus d mu. So minus the integral of gn minus d mu is going to increase to minus the integral of g minus d mu. And this is precisely the integral of g d mu. And that's what we wanted to prove. So this is a very nice exercise of getting used to working with the different convergence theorems that we have for Lebesgue integrals, because it looks similar to some of the other theorems that we've had, and you basically just apply, it uses a lot of really good techniques. Breaking functions up into their positive and negative parts is really useful because it's much easier to work with positive valued functions than it is to work with positive or negative valued functions. And this theorem also allows us to apply both the monotone convergence theorem and the dominated convergence theorem. So, yeah, this is how you do this exercise.